All right, we ready? All right. Sorry for the panic. I'm new here. I didn't know what the procedure was for this. I showed up at 11:30 and nobody was here. Okay. So I'm Amy Elliott. I work at the manufacturing demonstration facility. We're off on Hardin Valley Road. We're off campus. It's also known as the MDF. So if you hear MDF, that's us. We're funded by the Department of Energy to demonstrate these advanced manufacturing technologies. So our two main thrust areas are additive manufacturing and these carbon fiber and composites. So I'm going to do a little introduction to additive manufacturing. Who all has heard of additive manufacturing? Okay. What about 3D printing? Okay, it's all the same. Additive manufacturing, 3D printing, and rapid prototyping. They've actually recently changed the name from rapid prototyping to additive manufacturing because our material properties are so good that we can actually use the things we make with this technology as the final product. So let me show you a little video here. So the way it starts is you have your 3D model. So this is a CAD file, a CAD representation of your part. And the software slices it into layers. All right? And this is where the additive part comes in. So each of those layers gets sent to the machine one layer at a time. So we're doing a little dramatic effects here. Okay, so we wipe a layer of powder. This is one type. It's called powder bed fusion. Wipe a layer of powder, make that layer with a laser. Wipe another layer, make it with a laser. So we're building this part one layer at a time, additive manufacturing. All right, and the part grows in a downward motion, and when we're done, we dig it out of the powder bed, and our part is ready, for the most part. So the advantages of this technology, there's a lot of advantages. We have complete control over every little piece of that part. And as opposed to traditional manufacturing, which is subtractive, all right, where we're actually taking a bulk piece of material and carving away bits at a time until we get the part we want, we're adding material just where we want it. So so we're introduced to additive manufacturing. So I'm going to show you these principles of additive manufacturing. I'm going to go over some applications and then some thrust areas that we focus on at the MDF, and then some of our unique capabilities that I think you'll be interested in. So the principles of additive manufacturing, these were coined by Hod Lipson from Cornell. He just wrote this great book called Fabricated. You've probably heard of it if you're into 3D printing. So he coined these 10 principles of additive manufacturing. This is a really great way to describe the advantages of the technology. So the first principle is complexity is free, okay? So unlike traditional manufacturing where I'm limited by the angle or the size of my machine tool, we are not limited by what shapes we can produce. And actually, we're limited mostly by our CAD software, right? So our CAD software can't really do complex shapes like this very easily. So that's a big hole if any of you are interested in developing the next generation of CAD software. But just so it doesn't matter if I'm making this very complex shape or if I want to make a very simple block. It doesn't matter. The computer doesn't care. The machine doesn't care. Let me check my notes to make sure I'm not leaving anything out. Yeah. All right. So that's all for that first principle. The second principle is variety is free. So just like it doesn't matter how complex my part is, I'm not limited to one part at a time either. So I'm not limited to a batch of a single part at one time. Third principle, no assembly required. So I've got some toys to pass around here. Turns out if you get the dimensions right, you can actually build things all in one piece. No assembly required. So this is it looks like a metal bike chain. It's actually made of a photopolymer. This was printed last night. And it's actually printed just like this, as is. So I'll pass this around so you can see. And then another mechanism that we like to show off is this little gear set here. I'll pass this around to the other side here. And then the other part of this principle is of no assembly required is you don't have to make all these little tiny pieces to assemble. So this is actually an air duct here. And if you know anything about air ducts, you know that they come in a million pieces. There's so many different pieces. There's brackets, there's fasteners, there's pins, there's all kinds of things to make these things come together. But with this technology, we can not only reduce the part count, so I've got one piece instead of 50 pieces for this air duct here, but I'm also creating something that is very efficient. So this is actually a very efficient channel for my airflow. My airflow can travel much better through this. Fourth principle is there's zero lead time, so we don't need fixturing. We don't need any fixturing for this. You just print whatever you want. You just hit print. Zero skill manufacturing, I would like to say low skill manufacturing. We're not quite to the point where it's zero skill manufacturing, but we're getting there. Zero constraint. So this is these are one of my favorite 3D prints. It's by an artist her name is Bathsheba Grossman, and she actually designs these things using math. So she doesn't use a CAD program. She actually programs the shape using math equations. Compact, portable, affordable manufacturing. So we've seen a big uprising of these desktop systems, and they do a pretty good job. I mean, we're seeing that they're actually replacing the much bigger, much more expensive industrial systems. Less weight, less waste. This is a big one. So with this technology, we are actually putting material exactly where we want it, and we're not wasting very much compared to traditional manufacturing. So you see these turbine blades being built in an additive manner. So the material is going exactly where we want it. Infinite shades of material. So there's the type of technology that bike chain was printed is called polyjet, and it's an inkjet technology where you're actually inkjetting material. So instead of inkjetting an ink, you're inkjetting a photopolymer, and that gets cured with a UV light each layer at a time. So just like your inkjet printer at home can print multiple colors, right? So it has the three basic colors and then a black cartridge, and then it mixes those colors to make the shades in between. We can actually mix different materials. So we can have like a spongy, a rubbery material, and then a hard material. We can not only print those next to each other, but we can actually mix them and actually tailor the durometer of our material. And then Principle 10, precise replication. We're still working on better scanning technology. It'd be really great if any of you have an idea of how to get inside of a part. We have a Neutron source that we do that with. It's kind of expensive, but you can copy parts pretty easily with this technology. So what has this technology done for industry so far? Well, a big one is enabling the next generation of robotics. So the PETMAN project was a humanoid project with the Department of Defense, and it's this really great humanoid robot. And what additive manufacturing really brought to this was really compact joints. So we have this arm here. Let me point it out. And typically when you have hydraulic systems, this is a hydraulic system, you have these exterior hydraulic actuators that take up a lot of room. Well, if you don't want those, if you want your arms to be more nimble and take up less space, additive manufacturing really helps that because we can actually design these fluid channels within the joints. We don't have to do them on the exterior of the joint. And this is the O&L hand. You've probably seen this. It's on the cover of a lot of things. But it's a great example of what additive manufacturing can do for industry and for the way we design things. It's really changed the way we design things. So we have these fluid channels already plumbed in. We have the cavities for the motors already plumbed in. And I will pass around this part. So this is actually part of the arm that we're working on. And if you look inside, you can see the fluid channels already plumbed in there. So if you can imagine when you look at this, imagine trying to actually put those things in by hand. It would be pretty difficult. So there's a big advantage to printing it all in one piece. So another great application is aerospace. So aerospace actually, they tend to machine things out of solid pieces of material. well, obviously everyone does that, but they have a very high buy-to-fly ratio, right? Because they want to reduce their parts to very little mass as they can. So currently, the average buy-to-fly ratio is something 33 to 1. Because if you can imagine, you start out with a block of material that's, as big as that piece, and then you carve it away to just that one little piece. Well, with additive manufacturing, since we're just adding material exactly where we want it, we can reduce that buy-to-fly ratio 1.5 to 1, which is awesome, right? That's a great improvement. Another cool application is these turbine blades. So with additive manufacturing, like I said before, we can build things that we could have never built before. So this turbine blade actually has some cooling channels in it that are really intricate that couldn't be done with traditional manufacturing. And let me pass that around here. So here's one of these turbine blades. And I'll show you the interior of it in a few slides. And so that is actually, I believe that's made out of titanium, so we can actually do metals, which I'll talk about. So on top of these great applications that we are looking for, we're always looking for more awesome applications, we're working to advance this technology. So we want to develop more materials. So currently we have titaniums, Inconels, and stainless steels, but we want to expand that to all metals, obviously. We want to advance the controls. So currently these printers don't know what's going on while they're printing. It's not a closed-loop control system. Some of them will pick up on the fact that, oh, my build has fallen over, during printing, and it'll stop. But for the most part, no. So we're working on closing that control loop and making these machines smarter so that we can certify the parts and make sure that we get the geometry that we asked for. Finally, we're doing some benchmarking as far as which technologies can get how accurate, and then. So, and overall, just trying to develop new technologies, maybe new processes that are better and can do more materials. So, one of the unique capabilities we have here at Oak Ridge National Labs is this Neutron source. So we can use this Neutron source to actually scan our parts and figure out how well they were built, how well we could improve. So we've scanned this turbine blade, so you can see this fluid channel snaking through here. You can't make that any other way than additive manufacturing. And turns out this is a really great way to cool these. So we scan it with our Neutron source so we can get all the information about it. And then we can actually go through the part and look for defects. So if I wanted to use this on an actual engine, I can actually make sure that it's what I wanted, that there's no voids, there's no fractures, that kind of thing. So this is actually really, really cool. It's really important to be able to see inside the part like this. Okay. So as far as metal additive manufacturing systems, we have quite a few. We have quite a variety. We have both the powder bed systems, which is electron beam melting and laser powder bed. And I can answer more questions about those. Those are pretty popular nowadays. We also have the ultrasonic consolidation, which is where you're ultrasonically welding sheets of material together. And then we have this laser metal deposition where you're actually throwing a mist of metal vapor at a beam, and you're actually adding the material that way onto the part. And then as far as polymer-based systems, we're really, really heavy into the fused deposition modeling, which is that hot thermoplastic injection, or extrusion. So that's kind of like the hot glue gun one. That's the one you see on all the desktop printers, the MakerBots and that kind of thing. But we also do have the PolyJet, which is the inkjet of photopolymers. And then we have this really awesome system that I love, is the big Area Additive Manufacturing system. So this has an 8-foot by 8-foot by 8-foot build platform, and the nozzle is like 1/4 of an inch wide, so we can print a lot of plastic really quickly. So this is great for applications where you require large fixtures, perhaps, or maybe you need a large stamp mold. So you can see we can build some pretty big stuff with this. As far as the carbon fiber research that we've been doing, we found that if you add some carbon fiber to the materials, it can reduce warpage. So you see this is the neat ABS print, and you can see it curls during a build. You know, you think that, you know, you hit print and things will be nice and it'll come out great, but we actually see a lot of issues such as warpage, and warpage is a big one. So just by adding a little bit of carbon fiber, we can eliminate the warpage altogether and actually drastically increase our material properties, improve them. And then on the other end of the spectrum, so we have the big area manufacturing, now we have the small scale additive manufacturing. We have a lot of these desktop systems. We are currently trying to benchmark where we are as far as desktop printing and then project where we should be in the future, where we should go. And these are great for, you know, just some quick models and fixtures. And these are also great for new material development. So these are on the order of like, so this one's like $800. I can try a new material in this printer and not worry about destroying it because it's only $800. So that's really great for that. And then we can outfit them with new sensors. These systems are way more open than the larger industrial types, so we can try out new sensor technology with them really easily without so much risk. And then carbon fiber, again, on these small scale systems, just like I said, these are great for new materials. So we found that, again, adding carbon fiber drastically reduce the curl, but also adding carbon fiber can make the accuracy of these printers better than some of the industrial systems. So just by adding some carbon fiber or carbon material, we can drastically improve this technology on these cheap $800 printers. So it's really exciting. Another last point is the multifunction material system. So we're working on printing circuits, right? So we're printing conductives next to non-conductives. It's a big area. And then I'm going to leave you with these principles of additive manufacturing, and I want you to think about how additive manufacturing can help your industry, or maybe we can work together in improving additive manufacturing to help your industry. And with that, I will take any questions. Thank you. Yes?
So why does carbon fiber improve accuracy?
It's still up for debate, I think. Chad can help me. If, in my personal opinion, it's probably the heat transfer, or it's the viscosity as well. So like when you add particles to a fluid, you know, it's fluid when it's being heated, it'll make the viscosity better so it's not oozing around and it's just making it a little more accurate. Chad, is that okay? Who gives me the thumbs up?
Your first answer was more correct.
We
We don't know.
don't know. Okay. I have a theory, but yeah. Yes?
Question for you. No one else basically positioned in this field. You don't need the equipment, correct?
Not yet.
Not the fact, it's not the field, or develop materials, or develop the processes, and how to use the equipment. What is it specifically that no one else functions in this field?
Yeah, so far it's been working with existing technology and improving process parameters. Okay. But if I have any say in it, we will be developing new processes and new sensor technology for those new processes than the old processes.
How would someone interact with you?
Yeah, we are totally open to anyone who wants to work with us. I can give you my card. You can just contact me.
Where the relationship would be looking to learn from what's out there, what's already needed, to see how you can connect with, or
Absolutely, all of the above. So we are looking for anybody who wants to use the technology but maybe don't see quite the bridge, or maybe the technology is not quite suited for them yet. We can work with them to see what we can do on that side.
Can you comment on the MDF partnership awards that are coming from DOE that are enabling companies to work?
I'm not very well versed on the funding side. Chad, did you hear that?
I can't hear the question. I'm sorry. Could you comment on the MDF funding that you have coming from headquarters to enable collaboration and engagement?
Right, yeah, so we actually have money in hand right now from the Advanced Manufacturing Office to work with industry members. So this is as part of the manufacturing demonstration facility, emphasis on demonstration. That is to find application areas where industry is interested in this technology And by government standards, it's a pretty simple proposal process. It's only a couple of pages. Come up with an idea that will utilize about a man-month of time, of our time, and the government will pick up the tab for our effort. The two strings attached are that the company, the industry partner, needs to put forth the same level of effort on their side as we do on ours. So it's a dollar for dollar cost share in kind, so no money on the table. The other string is that it needs to be published at some level. So a portion of what we're doing needs to at least be publicly released. So if you have interest in that, talk to Amy afterwards or myself, and we can give you more info.
Thanks, Chad. Yes.
As far as manufacturing goes, I see the better, I see the cheaper, but what is the future outlook on faster? Compete with, say, heavy stamping parts.
So on the additive manufacturing side, so the limitation on the additive manufacturing side is really how much material we can either melt at one time or extrude at one time, or whatever the process is. So really, you have to go to improve the speed. It's more about scaling, right? So we have to, if you want something really fast but not so accurate, you can go with like the big area additive manufacturing. Does that answer your question? I'm not sure I completely understood. Okay. Yeah. Yes.
Well, somewhat related to that, in terms of getting an acceptable surface finish, where's the trade-off between doing secondary machining and slowing down the process to get a better surface finish?
That's a good question. I think that's a research project. I don't think there's an actual standards for that yet, but yeah, that's a great question. Certainly, if you're interested in, we have post-print machining capabilities for the big area additive manufacturing system. And if you want to explore the trade-off there, that's definitely something we'd be interested in working on. Yeah, I saw a hand up. Yep.
Yeah, how, like you have turbine blade, usually that will get a forged part. What does the strength compare on your process?
Yeah, I'm not exactly sure. What I've heard is something like 80%. Is that right, Chad?
Yeah, actually, for the titanium products, we're actually achieving wrought-like properties for stiffness, strength, and elongation. Now, when you go to creep, fatigue, fracture toughness type properties, it's a very fine-grained structure because we have very high heating and cooling rates. So, but we're still better than cast in most categories. So it is a true engineering material.